Welcome to Schrödinger's Chat, the podcast where I explore the real science behind the biggest questions in the universe, as well as some of the quirkier science we encounter every day. I'm Anna, a sixth form physics student with a lot of curiosity and a passion for understanding how the world works. From the smallest particles to the largest galaxies, join me as we uncover the mysteries and wonders of the universe and explore how physics shapes the world around us. Rare, beautiful, and almost magical. A rainbow is one of the few natural phenomena that doesn't need any explanation to make you go, wow. But understanding why it happens makes it even cooler. In this episode, we're doing a deep dive into a piece of physics magic, rainbows. How and why do they form? Why are they that shape? And could you ever find the end of a rainbow? Before we get started, a quick reminder to leave a review or comment if you like this podcast, and check out the podcast Instagram page, Schrödinger's Chat Podcast on Instagram. Here I post all sorts from extra bits relating to the episodes, STEM book recommendations, and various other general nerdy science stuff. If you like the podcast, you will definitely enjoy some of that stuff, so do go and have a look. Back to the episode. We're going to start with the very basics, and let's just talk about white light. So, of course, white light isn't white at all. It's made up of all the colours of the visible light spectrum: red, orange, yellow, green, blue, indigo and violet. Richard of York gave battle in vain, or Roy G. Biv. The first person to figure this out was Sir Isaac Newton in 1660, and you may actually remember a bit about this if you listen to the first Legends and Lab Coats episode, which I think was episode 8 of this podcast. This is his famous prism experiment, where he passed white light through a prism and it emerged as a full spectrum of the Roy G. Biv colours. Before Newton, people thought the prism somehow added colour to the white light. They thought white light was just white, and actually passing it through the prism is what added the colour. It was something about the glass. But Newton was the first to realise that the opposite was actually true. White light already contains all colours, and the prism just separates them. So how does this actually happen? Well, each wavelength of light bends or refracts by a slightly different amount when it passes between materials like air and glass, and that's called chromatic dispersion. Red light, which has the longest wavelength and the lowest frequency, bends the least, and violet light, with the shortest wavelength and the highest frequency, bends the most. This effect is exactly what happens to form rainbows, with all the raindrops acting as the prisms that refract the light. The different refraction of each wavelength is why red is always on the top of a rainbow and violet at the bottom. And a quick side tangent, whilst chromatic dispersion allows us to see these beautiful rainbows, it can actually be an issue in practical applications of light. For example, in optical fibres, which is a way of using light pulses to transmit information in thin fibres. With white light, the pulse would spread out due to chromatic dispersion, meaning the different colours of light would travel at different speeds, so reach the end of the optical fibre at different times, interfering with the signal. This is why monochromatic light is often used, light of one colour, especially over long distances, as over a longer optical fibre, the dispersion effect would be greater at the end. Although it does depend on the situation and how the optical fibre is being used, because sometimes multiple wavelengths of light are actually favoured, as you could send multiple pieces of information simultaneously. Anyway, side tangent over, back to rainbows. Okay, so we know how and why we get a whole spectrum of colours from originally white light, but how does this turn into a rainbow? To understand this, let's zoom in and think about what happens in a single raindrop. Let's picture our raindrop as spherical and suspended in midair. When sunlight hits it, several things happen. First, refraction, just like what we talked about earlier. The light slows down as it enters the water, and the speed of light in water is about 0.75 times that in air, so the change in speed causes it to bend. Now we can use Snell's law. By the way, this guy Snell, a Dutch astronomer and mathematician who devised this equation, had a magnificent name that I just have to mention. He was called Willebrord Snellius, or perhaps Dutch it could be like Willebrord Snellius. But personally, I think it's a real missed opportunity not calling this Snellius's law. I mean, that just sounds so magnificent. But anyway, Snell's law, which you might also know as the law of refraction, describes the relationship between the angles of incidence and refraction when a wave crosses the boundary between two different transparent media, in this case air and water. The angle of incidence is the angle to the normal at which light enters a medium, and the angle of refraction is the angle to the normal when it has passed into the medium. And by the way, the normal is just an imaginary line that is perpendicular to the boundary between the mediums. In equation form, Snell's law is the refractive index of the first medium multiplied by sine of the angle of incidence is equal to the refractive index of the second medium multiplied by sine of the angle of refraction. n1 sine theta 1 equals n2 sine theta 2. Now, the refractive index is essentially a measure of how much a medium refracts light, or technically it's the ratio of the speed of light in a vacuum to the speed of light in that material. Here, n1 and n2 are the refractive indices of air and water, and the angles tell us how the light bends. Now, I'm not going to bore you anymore with the equation and how numbers work out, but essentially, red light, which has a wavelength of about 700 nanometers, has a smaller refractive index than blue, which has a wavelength of about 450 nanometers. So red bends less sharply than blue. After entering the droplet, the light ray hits the back surface of the droplet, where some of it reflects internally, so the back surface is kind of acting as a mirror. Then it exits the front surface again, bending as it leaves. The slightly stranger but even cooler bit is how we perceive this light. Although light is bouncing around in every rain droplet, it only exists at very specific angles that focus most of that light towards our eyes. For the primary rainbow, which is the really bright one and probably the first one you see when a rainbow occurs, and yes, there are multiple, but we'll talk about that later, this happens at about 42 degrees for red and 40 degrees for violet. Now, if you're wondering where those numbers come from, when you trace a light ray through a droplet, the angle between the incoming sunlight and the emerging ray changes with the point of entry, and this is called the deviation angle. If you plot it, you can find that the deviation angle reaches a minimum around 42 degrees. That minimum sort of focuses a number of different angles, a large range of entry angles to the ray, which all produce rays that emerge around the same deviation. So that's where the light is most intense. This reminds me a bit of many-to-one functions in maths, where many inputs give the same output, but this time with many different angles giving the same emergent ray. Now a little bit more maths for you. If you take the derivative of deviation with respect to entry angle and set it to 0, you get what's called the rainbow angle. This is a stationary point in the geometry, which is the reason the rainbow has a clear edge rather than a sort of fuzzy, smeared edge. I bet you never thought rainbows had anything to do with calculus, but maths and physics are so cool that nature uses Snell's law, reflection, and a bit of calculus to give us a wonderful display of light and colour. Now, going back to those angles, 40 and 42 degrees, they are measured from what's called the antisolar line. This is basically the line running from the sun through an observer's eye and into your shadow on the ground. This point is called the antisolar point, which is the point directly opposite the sun in the sky. So if the sun is behind you, your shadow points directly along that antisolar line. The centre of every rainbow you see lies exactly along that line, meaning the rainbow is always opposite the sun in the sky. That's why you'll never see a rainbow at noon with the sun high overhead, as the rainbow would be below the horizon. This is also why rainbows are easiest to spot when the sun is low, like early morning or late afternoon, when the 42-degree circle of light actually cuts through the sky in front of you. So when you see a rainbow, you're really looking along that antisolar line opposite the sun, with the arc forming at that 42-degree angle all around it, and your head's shadow is technically at the centre of the circle. That's why rainbows are arcs, centred on the antisolar point, which is in this case the shadow of your head. So you could even think of it as your head being the centre of the rainbow circle. That's why when you see a rainbow, it always looks like you're seeing the perfect arc, like a semicircle. You always feel like you're seeing the centre of it. And yes, a rainbow is technically a full circle, but the ground and the horizon block the rest of the circle. So I'm afraid you cannot find the end of a rainbow. It's kind of weird to imagine rainbows as circles after only ever seeing arcs, but I promise it's true. In fact, astronauts flying above Earth have actually photographed complete circular rainbows from above. So when you see a rainbow, you're not looking at something that's just out there in the sky that's fixed in that position. You're actually seeing light from millions of raindrops that happen to be at exactly the right angle between you and the sun. Move your head even slightly, and you're seeing light from different droplets entirely. I think this is really awesome because it means the rainbow you see is personal to your perspective, and technically different to the one someone standing next to you would see. Alright, so we've already talked quite a bit about the order of colours in a rainbow, and how that depends on dispersion and wavelengths of light and all that. But I just wanted to quickly mention the colours we actually see in a rainbow. As we already established, red light exits the water droplets higher in the sky and violet exits lower. But between those two extremes, we still have all the intermediate wavelengths which spread out into a continuous band. Thinking about prisms, you might think the colours are sharp bands, as in there's a boundary between each colour, but they're actually a smooth gradient. Your eyes and brain just group them into categories. In fact, Newton originally only saw 5 colours in his prism experiment, not 7. He saw red, yellow, green, blue and violet. He added orange and indigo later, mainly to get a list of 7 colours. Newton and others at the time thought the number 7 held a lot of significance. There are 7 days of the week, 7 musical notes, 7 planets that were known at the time. In fact, he kind of associated the number 7 with harmony in the universe. Therefore, Newton liked the idea of 7 colours matching the 7 notes in a musical octave, so in his book Optics, which was published in 1704, his list of colours included orange and indigo to give a total of 7 colours instead of the original 5 that he actually observed. So going back to rainbows, in a sense, Roy G. Biv is our way as humans of categorising the visible spectrum, when in reality it's a continuous spectrum and a continuous physical process in a rainbow. The real rainbow is pure, with no defined sections or bands, just nature doing a little bit of trigonometry with some photons. Next, let's look at some of the extra features and effects that come with rainbows. First, double rainbows. A double rainbow forms when light reflects twice inside the droplet before leaving, so the light exits at a steeper angle, around 50 to 53 degrees, meaning the secondary rainbow is higher in the sky, or above the primary rainbow. With each internal reflection, the amount of light that is scattered back to the observer reduces, which is why the secondary rainbow is fainter, with the colours often even appearing pastel. The other distinctive feature of the secondary rainbow is that the order of the colours is reversed. Because there have been 2 internal reflections to produce the secondary rainbow, the order of the colours brought about by the first reflection is flipped to give the reverse order, with violet being the top colour and red being at the bottom. Also, secondary rainbows actually always happen, but because they are fainter and higher up in the sky, they are just much more difficult to see. Again, like we said earlier, your best chance of seeing a double rainbow is when the sun is low in the sky. If you can see 2 rainbows, you might notice that the region between the 2 is much darker. This region is called Alexander's Band, named after Alexander of Aphrodisias, who first described it in 200 AD. It's darker there because light rays at angles that are outside the range of angles forming the rainbow are reflected away from the observer, almost acting like a dead zone between the 2 reflection angles of the 2 rainbows, creating this dark band between them. But wait, there's more. If you've ever seen extra faint pastel fringes just inside the main rainbow, these are called supernumerary rainbows. These happen as a result of wave interference. When waves overlap, they can strengthen or cancel each other to give bands inside the primary rainbow. When the waves constructively interfere, a band is created, and in areas of destructive interference, waves are cancelled out and give little darker bands between successive supernumerary rainbows. The colours of these bands are not pure spectral colours, but often complex mixes of pastel colours. Because the size of the raindrop determines how much interference occurs, the spacing and brightness of those fringes actually tells us about the size and distributions of the droplets in the air. So the optical physics of a rainbow can actually tell you about the nature of rain or moisture in the air. Although I wouldn't use it as a weather forecast. By the time you've seen the rainbow, it'll probably already be raining or just have rained, so you may get soaked anyway. Still awesome though. Now, if you think rainbows are cool, wait till you hear this. Did you know you can get a rainbow at night? Well, if the sun's gone but the moon is bright and full, you can get a moonbow, a rainbow formed by moonlight. It follows the exact same physics and geometry, but because the moon's light is about 400,000 times dimmer than the sun, our colour vision doesn't really activate, so to our eyes, it looks white if we can see it at all. However, cameras can pick up the full colour, so astrophotographers take pictures with long exposure to capture photos of these moonbows. And it's really cool. I highly recommend that you look up moonbows or lunar rainbows, it's really awesome. Then there are fog bows, created when the raindrops are actually tiny mist droplets, which are only a few tens of micrometers across. Whilst rainbows are mainly due to refraction, fog bows' colour comes from diffraction. Diffraction is the bending or spreading of light waves as they pass through a narrow opening or around an obstacle. So when light shines on the much smaller water droplets in fog, diffraction becomes the main factor controlling the light's behaviour. This causes light to be scattered over a much wider range of angles than it would be with large raindrops. Because of this, the colours blur together and the rainbow becomes wide and white sometimes, with all of the colours blurring to form white light. These fog bows often occur out at sea where there is ocean fog, so they are apparently often referred to as white rainbows or sea dogs by sailors, and are sometimes seen as an omen of bad weather out at sea. Finally, there are circumhorizontal arcs, and these are really, really cool. Circumhorizontal arcs are often mistaken for rainbows, but are actually caused by ice crystals in cirrus clouds acting as prisms. It's the same physics as water droplets, just crystalline instead of liquid geometry. It's actually a little bit more similar to refraction and dispersion in actual prisms. Now, circumhorizontal arcs, or fire rainbows as they are sometimes called, and I think that is a slightly cooler name, are quite rare because the conditions for them to form are very specific. The sun must be very high in the sky, at an angle of at least 58 degrees above the horizon for this arc to form. This means it is not visible in countries at high latitudes above 55 degrees. In fire rainbows, the arc is a spectrum of colours with red on top, and then the rest of the colours arranged parallel below it to the horizon. It's often bright and very vibrant, sometimes appearing as a long, colourful band, and sometimes as only fragments if the cloud is patchy. It appears below the sun and is often located further away from the sun than a traditional rainbow. Now, I actually have experienced a fire rainbow, but I didn't realise it until researching and making this episode. It was a cold winter day in December 2023, and I was out for a dog walk when I noticed a bright, colourful patch in the sky. It definitely wasn't a rainbow. It kind of actually looked more like an oil spill, but in the sky. You know that rainbowy sheen you get when oil is spilled. But it was awesome, and I remember thinking at the time, what is this? Am I witnessing some strange magical event? And I took a few pictures on my phone because it was so cool, and also as evidence that it actually happened, because I did think I had witnessed something unique and possibly magical. Fast forward 2 years, and I'm sitting researching for this episode, and I'm reading about circumhorizontal arcs. What does that look like, I wonder? And I search up some pictures. Then, to my astonishment, came hundreds of pictures of the same thing I saw in 2023. So I go back through my own photos, and sure enough, it matches the Google images. I even searched up the latitude of the UK to check that it was possible to see fire rainbows in the UK. It turned out to be 54 degrees, so yes, the UK is just within the range of latitudes which can see the fire rainbows. If you haven't seen a fire rainbow, search it up, it's awesome. And also, I think I'm going to post my pictures of the fire rainbow on the Schrödinger's Chat podcast Instagram page, so go there if you want to see it. Anyway, I cannot fully describe the sense of satisfaction of finally discovering what it was that I had witnessed that day. I would be lying, however, if I said I wasn't just a little bit disappointed that it wasn't in fact magic. But, maybe physics is magic after all. So, I hope you've seen that rainbows are more than just meteorology. They're a natural intersection of optics, wave theory, and even calculus. You could even argue quantum mechanics comes into it somewhere with interference of light. From this, they are an awesome natural example of light behaving in many ways, wave, particle, and everything in between. There's also a poetic side to that physics too, in the fact that everyone sees their own rainbow. The one you see is made from a completely different set of raindrops than the one the person next to you sees. That's awesome from a physics perspective, and also just so beautiful. Either way, we can all agree that rainbows are A, awesome, and B, beautiful. So next time it rains and the sun appears, remember you're not just looking at a meteorological event, you're watching sunlight slow down, bend, and reflect through the powers of geometry and optics to make art. And like when I thought that maybe that fire rainbow was magic, I think rainbows are one of those phenomena that feels close to magic. Again, just proving that maybe this universe's version of magic is just physics. That's all for today. Thank you so much for listening. I hope you have enjoyed this episode. If you have, leave a comment or review this podcast and head over to the Instagram page, Schrödinger's Chat Podcast. Also, specifically for this episode, go and have a look just to check out my fire rainbow pics. I'll catch you in the next episode, but until next time, stay curious, and next time you see a rainbow, remember that behind the beautiful colours, there's even more beautiful physics. Bye!